Welcome. In the last section, we built our wah-wah filter in analog electronics. In this section, we'll continue to build the same wah-wah filter in digital domain. As you are aware, wah-wah effect is nothing but a bandpass filter, and in digital domain, this is how a second order bandpass filter looks. The filter has feed-forward coefficients, B0, B1, and B2, and it has got feedback coefficients called A0, A1, and A2. When we solve this transfer function and convert them into a difference equation, this is how it looks. So here X stands for the input to the filter and Y stands for the output of the filter. And as you have already seen, these coefficients are getting multiplied by inputs and outputs. And what these time indexes are meaning is that N is the current input sample, N minus 1 is one step before that, and N minus 2 is two steps before that. So these are past samples of the input. And Yn minus 1 depicts one sample of the output from the past, and this is going back two steps. So basically, it's a combination of current and past samples of the input as well as the output, multiplied by suitable coefficients. So now I'll import some libraries and I'll get started. So first we define our parameters. And in current case, we will take a sampling rate of 44.1 kilohertz, which is very typical in audio industry. And we will decide the duration of the signal to be 2 seconds. So we will define then the time axis, which is nothing. It starts from 0 seconds. It lasts till the duration of the signal. And it has the total number of sample that this time axis contains is the multiplication between the sampling rate, that is 44.1 kilo samples multiplied by the duration, which is 2 seconds. And this will create our time vector. So let me run the code. Once this time vector is created, we will create an input to this filter. And our input is a combination of two sine waves. One sine wave is at 220 hertz, which is the exact half of the A note in music. And the other sine wave is at 440 hertz. So we have these two sine waves that are the input to this filter. So now we'll define some filter parameters. We know that our filter center frequency is F0, and this center frequency is required to vary in accordance with the pedal. So we don't have a pedal here, so we are going to use an oscillator to simulate this variation, and I'll explain it later how. BW is the bandwidth of the filter, and if you remember, this bandwidth decides the Q factor. So we would like to have our quality factor as high as possible to make the filter response spiky. And that means that at resonant frequency, the filter gain is going to peak up. We have already defined the sampling frequency, and we'll define the normalized digital center frequency as 2 pi multiplied by the center frequency F0, which is the analog frequency, divided by the sampling rate. So this becomes our omega naught. So this is exactly what has been done here. I have my Q is 15. This is what I've taken. And my minimum frequency that I want to cover, that is the minimum center frequency of the bandpass filter, is 50 hertz. If you remember, the lowest note in the guitar is at 84 hertz, which is the open E string. So I would like to go slightly below that and cover that 84 hertz. And my center frequency of the bandpass filter should sweep up to almost 2 kilohertz, covering the entire guitar spectrum. And since I don't have a pedal with me, so I'm simulating a low frequency oscillator, which is going to swing between these two frequencies. And that low frequency oscillator is defined like this. So I have Fmin, which is 50 hertz, and then I have a difference of Fmax minus Fmin multiplied by 0.5, and this is what is the sweep rate of the wah filter. Basically, it is emulating the pedal motion of the mechanical pedal. So basically, we are going to be sweeping our center frequency of that bandpass filter at 2 hertz rate. Now we are going to initialize some buffers so that we can save our output, and I would also like to save my all the coefficients. So if you remember, for each center frequency there will be a different set of coefficients, and I have so many different frequencies starting from 50 hertz going up to almost 2 kilohertz. So I'm going to have many frequencies, many center frequencies in between. And for each of these frequencies, my coefficients are going to be different. So I want to save all of them. So I have defined some registers here, some arrays here. And I have also got to define my pass samples of input and output. So my x1 and x2, that is the pass sample of input, as well as my pass samples of the output y1 and y2 are initialized to 0, and then we'll progressively build them up. So let me just run this code and also create arrays. Now from theory, we know that we need to now calculate the filter coefficients, and I'm not going to explain how these formulas have been arrived. They are pretty much clear in the theory. So we start with the alpha. Alpha is nothing but the sine of the center digital frequency. If you remember, we have calculated it here, this part, and this is what is going to define the alpha. So here I have implemented omega naught. And once this alpha is available, then forward quotients are nothing but B naught is just alpha, B1 is 0, and B2 is minus alpha. That's pretty straightforward. And the feedback coefficients are 1 plus alpha, A1 is equal to 1, A1 is minus 2 cos omega naught, and A2 is 1 minus alpha. So these are standard formulas from the textbook. And once these coefficients are available to us, we divide all of them by A naught to normalize the filter. So this is what the normalized coefficients look like. So this is what I am going to now implement in the code. So I will start a for loop, which will go through each and every sample of the input signal, starting from the first one. So I initialized my center frequency. My center frequency is the first element of this array. If you remember this, I had initialized this array here, which is basically nothing, a sinusoid of starting from 50 hertz going up to 2 kilohertz in a sinusoidal fashion, defining the mechanical motion of the pedal. And based on that center frequency that I've chosen, I'm going to define my omega naught, and that omega naught in turn is going to define my alpha. So I have calculated this step, and then I will calculate all my coefficients based on the formulas given above. So we have these formulas, they have just simply been implemented in code here. And then I'm going to normalize them. So all of these coefficients are going to be divided by A naught, and they are going to get normalized like this. So here is a normalization step. And then I'm going to save all these coefficients. Remember, for every center frequency, there's going to be a different coefficient, and I don't want to lose any one of them because I need them for plotting later on. So I'm going to save all of these coefficients in the empty arrays that I had defined here. And then I'm going to implement my filter. So I will first initialize my input. My input is the current input sample. So if you remember, my input signal was a sinusoid, a combination of two sinusoids, and it was defined here. So I'm going to take the first sample of it and feed it in my filter. This is what this code is doing here. So first sample of that input has been taken and has been initialized as input to the filter. And then I'm going to implement the difference equation of the filter. So this equation is nothing, but if you see, x naught is the current input sample, x1 is 1 step past input sample, x2 is 2 steps past input sample, and then y1 is 1 step past output, and y2 is 2 steps past output. And this is what is the difference equation, which comes straight from here. This is the equation of the bandpass filter difference equation, and this is what I have implemented here. And once that equation has been implemented, I will get the first output from the filter, and that output is required to be saved. And I'm going to save that output in this output signal buffer that I had defined here. And then I'm going to update my inputs and outputs and prepare them for the next iteration. So my x2 will become my previous x1, my x1 will become my current x0, similarly my y2 will become my y1, and my y1 will become my current output of the filter. Basically, it's a circular buffer, and I need to continue to update them for the filter to keep running. So this is for the first input of the filter, and this entire for loop is going to run for all the center frequencies and for all the samples of, for all the input samples to generate the output. So let me just run it. And then I'm going to save my input and output signals for comparison in WAV files. So I have defined a file called filter.input, filter-input.wave, and I'm going to save my input signal. Remember, these were a combination of two sinusoids. And then I'm also going to save the output of the filter, which hopefully should have that wah-wah effect that we are talking about. So let me just run this piece of code, and let's see how these signals appear. So this is my input, and let me just run this file, and I hope you'll be able to hear. So this is just a combination of two sinusoids. One is oscillating at 220 Hertz and the other is oscillating at 440 Hertz, as I showed you earlier. And let's see what is the output of the filter. Clearly, you can hear that vocalization that is happening because of the sweeping of center frequency of the bandpass filter. Hear it again. So we know that wah-wah effect is being applied. And now I want to visualize this entire thing. So firstly, I want to see the center frequency of my bandpass filter, whether it is sweeping or not. So for that, I have initialized a plot where I'm just generating the magnitude plot of the filter. And let's run this code. So here we are. On the x-axis, we have frequency going from 0 Hertz to 2.5 kilohertz. And on the y-axis, we have the magnitude. And what you see here is the filter response. It's the magnitude response. And since we are simulating, if you remember, we are simulating the mechanical motion of wah using this. And what it is doing is, it is taking the center frequency from 50 Hertz to 2 kilohertz in a sinusoidal manner. So this filter is shifting its frequency from 50 Hertz, you can see it here, and going up to almost 2 kilohertz. And you can clearly see that the shape of this filter response, magnitude response, is very peaky in nature, and that's because we have selected Q as 15. So working perfectly fine. I would also like to plot a spectrogram of this output signal. So let me just run this code. Here is a spectrogram. So what is spectrogram? A spectrogram is a time versus frequency versus time plot. So on my x-axis, I have time axis, and on the y-axis, I have a frequency. And if you see, my signal was for the duration of 2 seconds. So this is x-axis is for 2 seconds, and I am plotting frequencies from 0 Hertz to 5 kilohertz, and I want to understand what is happening here. So, and this color code is basically all strong signals are tending towards yellow, and all weak signals, weak in power, are tending towards blue. That's what is the meaning of this spectrogram. And one thing that you'll clearly see here, that the high energy is concentrated in this lower part of the plot, and that's expected because we have a 220 Hertz signal in the main component, and we have a 440 Hertz signal, a sine wave, which is all seen here. And in addition to that, we have a sweeping pattern here, if you see. And this sweeping pattern is actually, if you see, is happening at 2 Hertz. There are 2 troughs here in first 1 second, and there are 2 troughs here in the next 2 seconds. So the frequency of this sweep is 2 Hertz, and that's not surprising because we have kept our wah rate at 2 Hertz. This is what, basically we are pressing the mechanical pedal twice in 1 second. That's what it is doing. So this center frequency is changing, sweeping from 0 to 200 twice in 1 second, and that's what this sweep reflects. And it is very clearly captured in the spectrogram. So in summary, we have been able to generate a sample signal. We implemented a bandpass filter. We implemented a wah-wah effect, and we've been able to visualize the filter behavior and its output spectrum. Hope you have learned from this, and I will see you in the next tutorial.